So look at factors that affect uh, possible reactions, and specifically here we shall look at temperature. We shall look at catalyst. We shall look at pressure, and then we shall look at inert gas. Basically, these are the factors that we shall look at that affect a reversible reaction. Then there is also what we call concentration. So we shall also look at experiments to determine the equilibrium constants. That is basically Kp and Kc. This is in terms of concentration. This is in terms of partial pressures. And then we shall look at the calculations involving Kp and Kc. And then if you look at the calculations involving Kp and Kc, we shall also look at how you write the expressions themselves. The expressions. Now, the purpose of this video, there are instances where learners fail to interpret the questions on the calculations. And when we wind up with this session, you'll be able to answer some of the questions that are related to chemical equilibria. What is most important in this topic is you need to know the factors and how the factors affect a reversible reaction. And then you should know the experiment to determine the equilibrium constant Kc and Kp. But mostly we look at the one for Kc in terms of concentration, and then the calculations in terms of Kp and Kc. Take for instance, I think we shall begin with a little bit of looking at how the factors affect the rate of a reversible reaction, position, okay, of the equilibrium, and then the value of the equilibrium constant Kc and the Kp. Okay. So as we proceed, when you are looking at factors affecting reversible reaction. Take for instance, if you have an equation, sulfur dioxide gas reacting with oxygen is giving us sulfur trioxide gas. Then they give you the energy value as being exothermic. This is negative X kilojoules per mole. When you are attempting such questions, you always look at the energy value that is attached at the extreme right of the equation. Because basically here, we are looking at a factor called what? Temperature. Okay? Temperature. Now, temperature affects a reversible reaction based on whether the reaction is exothermic or endothermic. For exothermic reactions, these are reactions that proceed by giving out heat to the surrounding, and they have the magnitude of negative sign. So whenever you see a negative sign at the extreme of the equation, it means that this reaction is exothermic. So, how do you explain the effect of such? It means that this reaction, the forward reaction, is exothermic. Therefore, exothermic reaction is proceeded by giving out heat. It means that increase in temperature does not favor the forward reaction, but rather it favors the backward reaction, because the backward reaction is endothermic and the forward reaction is exothermic. Exothermic reactions give out heat, therefore they are favored by reduction in temperature. So for this, it means that increase in temperature, okay? Increase in temperature, because these equations we are given questions to give the effect of increase in temperature on the yield of sulfur trioxide. So you realize that since the forward reaction is exothermic, when you increase the temperature, because the forward reaction is exothermic, increase in temperature will favor the backward reaction, meaning that the level of the sulfur dioxide decreases, meaning that the sulfur trioxide is going to decompose to give us sulfur dioxide and oxygen gas. Okay? So the rate of formation of sulfur trioxide decreases when you increase temperature. But the decrease in temperature will increase the yield of sulfur trioxide, shifting the equilibrium from left to right. That is in case you decrease the temperature. But increasing the temperature will shift the equilibrium from the right to the left, because the backward reaction is endothermic. Okay? Now, what effect? Temperature has an effect on the equilibrium constant value. That when the equilibrium shifts from the left to the right, okay, Kp value and the Kc value will have to increase. But if the equilibrium shifts from the right to the left, the equilibrium constant value Kp and Kc will have to decrease, because you are decomposing this, you are forming the reactants instead of forming the products. So it is very important for you to take note of how the factor temperature affects. That is one, that is temperature. So when you are given a value which is positive, kilojoules per mole, kilojoules per mole, then it means that if this is positive, you will have to look at, means that the forward reaction is endothermic. Okay? So means that increase in temperature increases the rate of formation of sulfur trioxide, because the forward reaction is endothermic. What does it mean? It means that the equilibrium constant value Kp, okay, and the Kc will also increase. But the backward reaction, in a similar way, it is exothermic, meaning that when you increase the temperature, okay, the forward reaction proceeds, but the backward reaction will be exothermic. Okay, so that's how you look at it. Two, when you are looking at what we call pressure majorly affects gaseous reactions. For example, this one, a case in point, this is a gaseous reaction where the reactants and the products are both in gaseous state. What does it mean? When you increase pressure, the reaction tends to move to the side where there is decrease in volume or number of number of moles. For instance, if you are given such an equation, explain how increase in pressure affects the reaction. Meaning you go back to the equation and see. If you look at the reactants, these are 2 moles plus 1 mole, which is here. This gives us a total of 3 moles. If you look at the product, it's having 2 moles. So there is a decrease in what? In the number of moles or volume. According to Avogadro, says gases do react in volumes, but of course you can also use the number of moles. So you realize that for this reaction, increase in pressure, it increases the yield of sulfur trioxide. Why? This is because the forward reaction proceeds by decrease in number of moles. Okay? The forward reaction proceeds by increase in number of moles. Therefore, the equilibrium position will shift from the left to the right. Okay? Shift from the left to the right. However, it has no effect. Pressure has no effect on Kp and Kc value. It has no effect on Kp and Kc value. It is only temperature that has an effect on the equilibrium constants Kp and Kc. Is it okay? So, if you look at this critically, this is when you increase pressure. So, increase in pressure tends to shift the reaction to the side where there is decrease in number of moles or decrease in volume. However, when you decrease pressure, it means that increase in volume. So, decrease in pressure will reduce on the formation of sulfur dioxide. However, the equilibrium will shift from the right to the left. Okay, why? Because the reactants have more number of moles than the product. So the reaction shifts to the left. Is that clear? So that's how you look at that is pressure. Then the third one is concentration. According to the Keteria's principle, concentration tends to look at if you are given the equation, for example, this very equation given to us, when you tend to increase the concentration of any of the reactants, okay? So what you have added always reacts to form the product, okay? So it means that when you increase the concentration of oxygen, what will happen is that more of the oxygen is going to react with sulfur dioxide to form sulfur trioxide. Okay? So the equilibrium will shift from the left to the right. In other words, increase in one of the constituents or one of the reactants or one of the substances or one of the species that is reacting. The reaction tends to shift to the side that removes what has been added. For instance, when you increase the concentration of sulfur trioxide, it means that this is going to destabilize the equilibrium. Remember, this is a reversible reaction. It means that what is on the left is balancing with what is on the right. So when you shift the concentration of sulfur trioxide by increasing it, it means that more of this has to decompose to give us sulfur dioxide and oxygen gas, so as to maintain the equilibrium. Okay, so that's what you are trying to mean by concentration. Though they always ask this question: what will happen to the yield of sulfur trioxide when the concentration of oxygen is increased? Definitely, increase the concentration of oxygen, okay, means that more of the oxygen is going to react with sulfur dioxide to form more of the sulfur trioxide, such that the equilibrium is stabilized. Okay, so that's what you look at. Then there is this other factor called catalyst. See, a catalyst favors both forward and, for example, this equation is favored by a catalyst called vanadium pentoxide. Okay, so the catalyst will favor both forward and backward reaction. Okay, but it does so by lowering what we call the activation what? It lowers the activation activation energy. But as I said, Kp and Kc is not affected by concentration. Neither is it affected by the catalyst. The catalyst, it increases both the formation of the forward and the backward reaction. Favors both, okay? Because you are aware that a catalyst alters the rate of chemical reaction, but remains chemically unchanged at the end of the reaction, okay? But does so by lowering what we call activation energy. Minimum amount of energy required to initiate a chemical what? A chemical reaction. And this does so by creating an alternative route through which the gases can get absorbed too. So these are some of the factors that you can look at if you are looking at the factors that affect the reversible reactions. There is a question that I wanted to look at. There's a question that says sulfur dioxide decomposes according to the following equation. Sulfur trioxide gas, decomposes. This one will give us sulfur dioxide gas plus oxygen what? Gas. According to the following equation, the energy value is enthalpy change. This is plus, okay? Plus positive. And therefore, if you look at this is a 2, you have to put here a 2. So they are saying state the conditions for the reaction. One of the questions was state the conditions for the reaction. For this reaction to proceed, okay, you look at the conditions. You have to be very careful when you are stating conditions, okay? So one, look at this. The reaction is proceeding endothermically. If it is proceeding endothermically, it means that one of the conditions is high temperature. High temperature. This needs high temperature because for you to decompose this, you need extremely high temperature. It has even been indicated. Two, you look at this. You are not just going to give these factors because you have read them and you have to give them. No. You have to look at the equation. That's where grammar cannot come in here. This equation is being favored by high temperatures because the reaction is endothermic. High temperatures. Then you look at, if you look at the factor called pressure, you realize that if you look at the forward reaction is favored by, this is increase in number of moles. Therefore, it means that the second one is low pressure. Low pressure. Now, students can go ahead and talk about the catalyst, which is vanadium pentoxide catalyst, because this catalyst here, it favors both forward and backward reaction, okay? So somebody can also talk about it, vanadium pentoxide catalyst. So those are some of the conditions that favor this kind of reaction. The question I was looking at is 2016, I think. Somebody wanted me to make, that's what I said, let me make some of the a hint on this. So this is what we look at. Then another part of the question was saying, write an expression for the equilibrium constant. Equilibrium constant Kp. So if you are writing the equilibrium constant Kp, you come here and say Kp is in terms of partial pressures. So it is the product of the partial pressures, okay, of the products divided by the partial pressures of the reactants raised to their stoichiometric powers. So this is partial pressure of sulfur dioxide, okay? This is squared multiplied by the partial pressures of oxygen over partial pressures of sulfur trioxide squared. You can write it like this, or a student can say Kp is equals to partial pressure of sulfur dioxide squared multiplied by partial pressure of oxygen divided by partial pressure of sulfur dioxide. This is squared. So that is the expression. And then they're saying when sulfur trioxide was heated in a closed vessel at 270 degrees Celsius and 0.25 atmospheres. 0.25 atmospheres. Okay? 46% of sulfur trioxide was decomposed at equilibrium. 46% of sulfur trioxide was decomposed at equilibrium. So you first of all look at this. You look at what the question, what they have given you was decomposed 0.25. So you come and see moles, initial moles, look at them critically. So if you have these 2 moles, okay, 2 moles, you don't have this, these ones are not known. 2 moles of sulfur dioxide decomposed, okay? So assuming the number of moles that reacted for sulfur trioxide will be X, meaning this is going to be 2X, this is going to be X. Moles that are remaining at equilibrium, this will be 2 minus X, okay? Then this will be 2X, this is going to be X. So they said moles that decomposed at equilibrium, meaning we shall say, since at equilibrium, these are being the number of moles that are remaining. So we shall have 2 minus X is equals to 46 out of 100. So this is 2 minus X is equal to, this is 0.46. Okay? So X is the same as 2 minus 0.46. So when you find this X, this will be the number of moles that reacted. So you get the number of moles at equilibrium. Okay? So after getting the number of moles at equilibrium, later on you get what we call the total moles. Total moles will be the same as you get 2 minus X plus 2X plus X. Already when you get this, the next, because they want you to calculate Kp, you go ahead. Okay? You go ahead and calculate the total, you get to calculate the partial pressure of sulfur dioxide, which is the same, sulfur dioxide, sorry, which is the same as number of moles, okay, which will be 2 minus x over the total moles times the total, which is 0.228. So when you do that, you also get the partial pressure of sulfur dioxide, which will be 2x, already you know x over total moles times the total partial pressure. Then you also get the partial pressure of oxygen, which will be x out of total times times not 100 times 0.28. So when you finish getting the partial pressures, you go back and feed it, okay, in the expression for Kp. I think when you feed it in the expression for Kp, you'll be able to get the equilibrium constant Kp. Now you look at the units. Look at the units critically. Units are very important as you are writing, because if you have this, you are going to square this, okay? So this will be atmosphere squared multiplied by atmosphere divided by atmosphere squared. So you realize that the units here are going to be in atmosphere. So after finishing this, you can be able to substitute and get you get the answer. So basically, there are many questions that you can find related to the calculation, but for this particular one, there is where they say moles at equilibrium, but they say decomposing. Okay, so if they said it was decomposed, then it means that you are supposed to get this, you equate it to the percentage, okay, of the sulfur dioxide that decomposed for you to get the answer. I think that is that for that particular. That was the one for the calculations. That was for the calculation.